Welcome to the DIY Honda Garage channel. DTC P064A indicates a malfunction in the high-pressure fuel pump system. This issue affects the vehicle's fuel injection process, leading to possible performance concerns. The fuel pump's role is vital, supplying high-pressure fuel to the engine for combustion. This malfunction can prevent the engine from starting or cause intermittent performance issues when driving. In this troubleshooting guide, we will review various diagnostic steps to isolate the exact source of this error. These steps include verifying the issue, checking components like the injector relay, measuring voltages across specific connectors, and ensuring there are no open or shorted wires in the system. DTC P064A refers to a high-pressure fuel pump system malfunction, indicating that there is an issue with the high-pressure components responsible for delivering fuel to the engine. The high-pressure fuel pump is critical for maintaining the necessary fuel pressure for optimal engine performance. This system primarily includes the fuel pump itself and the related wiring connections. The injector relay, located in the underhood fuse/relay box, controls the power supply for the fuel pump. When diagnosing this issue, it's essential to check individual components for faults and ensure that there are no interruptions in the electrical supply or connection failures that could cause a malfunction. Several potential causes can result in DTC P064A. A faulty fuel pump relay may not provide adequate power to the fuel pump, preventing it from operating correctly. Open circuits in the wiring can interrupt the electrical flow necessary for the fuel system to function, while short circuits may create unintended paths for current, leading to malfunctions. A defective high-pressure fuel pump can also contribute to this diagnostic trouble code, as it may fail to generate sufficient pressure. Additionally, issues within the powertrain control module, PCM, can affect how the fuel pump operates. It is crucial to systematically check each of these causes to determine the specific failure point. The symptoms associated with DTC P064A can vary, but often include failure to start the engine. When the high-pressure fuel pump system malfunctions, the engine may cranking but not start, frustrating drivers. Intermittent power loss while driving and poor engine performance, such as slow acceleration or stalling, can also occur if the fuel system is not delivering the appropriate fuel pressure. Drivers might observe these issues sporadically, which can indicate that the error is intermittent. It is essential to check for recorded DTCs like P064A in the vehicle's memory, which reveals that the problem has been detected, helping guide the troubleshooting process. The initial troubleshooting step involves setting the vehicle to the on mode, ensuring that all systems are powered. Once confirmed, use the HDS Honda Diagnostic System to clear the DTC memory, which resets any error codes. After clearing, attempt to start the engine. If the engine does not start and you are using a traditional key system, continue to crank the engine for up to 20 seconds. After attempting to start, check again for any pending or confirmed DTCs with the HDS. If DTC P064A appears, the issue is confirmed, and one can proceed to the next diagnostic step. In the second troubleshooting step, it is crucial to assess whether the engine started successfully in the previous step. If the engine starts, it suggests that the issue might be transient, and one can advance to further diagnostic steps, specifically Step 11, to explore deeper concerns. If the engine fails to start, additional checks are necessary, requiring you to progress to Step 3, which focuses on verifying the condition of the injector relay. This step brings clarity to whether the failure is consistent or if intermittent issues could be at play. The third step in troubleshooting DTC P064A requires turning the vehicle to the off mode to safely remove the injector relay. This relay is crucial as it controls the power supply to the fuel injectors, making it vital for the engine operation. Once removed from the underhood fuse relay box, test the injector relay for functionality. If testing reveals that the relay is functioning correctly, you can proceed to troubleshooting step 4. Conversely, if the relay is found to be faulty, replacing it is necessary, as it may be preventing fuel injection, thus causing the malfunction. Step 4 requires turning the vehicle to the on mode again, with the injector relay disconnected. The purpose here is to measure the voltage between specific test points, specifically between injector relay 4P socket number 3 and body ground. It is vital to confirm battery voltage at this stage. If battery voltage is present, the electrical path is intact, allowing you to progress to the next step to further diagnose the issue. Should there be no voltage detected, this indicates a potential open circuit in the IGP wire that needs repairing to restore the fuel pump functionality. In this 5th step, the vehicle should again be turned to the off lock mode. Measure the voltage at injector relay 4P socket number 1 while it is disconnected from the rest of the system. This test aims to determine whether battery voltage is present between this test point and body ground. If voltage is confirmed, it indicates the circuit is functional, and you can move on to step 7 for further voltage checks with the injector relay. However, if there is no voltage detected, it signifies the presence of an open circuit requiring repair in the +B INJ wire pathway between the injector relay and fuse number A12. In step 6, focus on inspecting fuse number A12, a crucial 20-amp fuse located in the underhood fuse/relay box. Ensure that the fuse is intact and has not suffered any blowout that can interrupt the fuel system's power supply. A non-functional fuse could disrupt the energy needed for proper operations. If the fuse is intact, further investigation is warranted to check for potential shorts in the +B INJ wire or the INJ RLY out ING wire connecting the injector control module and the fuse. If the fuse is blown, replace it immediately to restore functionality. Moving to step 7, reactivate the vehicle in the on mode with the injector relay disconnected. This step involves checking the voltage between injector relay 4P socket number 3 and socket number 4. The aim is to confirm whether any voltage is present. If voltage is detected at this stage, the test further tells us that the wiring and relay are functioning properly, allowing us to advance to step 9. Conversely, a lack of voltage here indicates a potential issue, mandating a check for any open wire situation in the INJ RLY line that might obstruct proper fuel delivery. During step 8, turn the vehicle back to off lock mode. The focus shifts to establishing continuity checks for the INJ RLY line. Begin by jumping the SCS line with the HDS and wait at least 1 minute. Disconnect PCM connector A before checking for continuity between the injector relay 4P socket number 4 and PCM connector A number 17. Demonstrating continuity indicates that the INJ RLY wire is in good condition, prompting a review of other potential areas like poor connections or loose terminals in critical connections. If these connections are confirmed as sound, substituting a known good PCM can be a next step, observing whether the DTC resolves upon replacement. In step 9, the vehicle should again be turned off. The procedure entails disconnecting the injector control module connector D, 4P, and creating a junction by connecting terminals of the injector relay 4P socket. Testing will focus on whether battery voltage is present between the connector A on the injector control module and body ground. This evaluation is crucial, as it determines the status of the INJ RLY out IGEDU1 wire. If battery voltage is confirmed, it allows us to advance to the next step. However, if voltage is absent, an open condition in the wiring may be present that needs repairs to restore signal continuity. Step 10 involves continuing to gauge voltage output from the injector control module by measuring between different test points. The goal is to check for voltage at injector control module connector D, 4P, number 2, against body ground. Confirming the presence of voltage indicates that the injector relay and its control are functioning properly. Should voltage be absent, this can signal an open wire issue within the INJ RLY IGEDU2 line infrastructure. Therefore, repairs should be executed to get this essential signal pathway operational again, ensuring proper functionality of the fuel pump system. For troubleshooting step 11, it is essential to rectify any preliminary test actions taken previously with connector reinstances. The next move involves jumping the SCS line with the HDS and waiting more than a minute as a protocol. After reconnecting the injector relay and the injector control module connector D, use a continuity check to examine connections between the specified test points. Confirming continuity between the injector control module's pin helps establish that signals are properly routing through the HPTI wire. If any continuity issues emerge at this stage, it indicates further open conditions or connection failures requiring immediate troubleshooting efforts. In step 12, the vehicle should still be in the off mode while preparing to check continuity for the FPF line. This system component lies between the PCM and the injector control module, and measuring the continuity between the test points will indicate the system's operational status. Confirming continuity here indicates that this critical connection is intact and functioning appropriately. Should there be an absence of continuity, that necessitates repair of the wiring within the FPF line to restore the seamless communication and control necessary for the high-pressure fuel pump's effective functionality. The focus of step 13 is verifying continuity in the fuel pump operational area. Disconnect the necessary connectors and focus on determining the continuity between the injector control module connectors. The aim is to ensure that the pads remain intact without any sign of failures that could lead to DTC P064A. Confirm continuity signifies that the connections are intact between injector control module connector D, and if failures emerge, it guides toward repairing potential open circuit areas that can impede fuel delivery and compromise vehicle performance. In troubleshooting step 14, the focus shifts to the continuity check for the FPF line, emphasizing connections specifically to the high-pressure fuel pump system. The approach involves disconnecting the high-pressure fuel pump 2P connector to evaluate connectivity with the injector control module. If troubleshooting points show continuity is obstructed, repairs are essential in the FPF wire to restore a seamless flow of power to the fuel pump. Ensuring integrity in the wiring harness directly impacts fuel delivery efficiency, crucial for the operation of the engine, thus confirming effective system performance. During step 15, maintain focus on verifying open wire conditions within the fuel pump system. Continuity checks will be conducted between tested points, specifically in relation to the high-pressure fuel pump and injector control module connections. Finding absence of continuity suggests wiring issues that can jeopardize the electrical circuit, hindering fuel pump operation. Ensuring robust connections within these critical nodes fosters accurate communication across the system, while addressing identified issues ensures overall performance is not compromised. If needed, substitute known good components for further verification to establish baseline functionality. In step 16, voltage measurements resume while the vehicle is on, to analyze consistency and detect shorts within the HPTI wire. Testing points need to be evaluated at specified connectors, primarily connecting the module to the PCM ground, allowing insight into potential circuit failures. When encountering voltage presence, immediate repairs to shorts or erroneous connections are necessary to mitigate risks affecting fuel system performance integrity. Through well-structured testing and protocols, one can ensure electrical networks maintain optimal functionality while identifying vulnerabilities within the entire circuit framework. The 17th troubleshooting step mirrors voltage assessments made in previous steps, focusing explicitly on the FPF line while keeping vehicle integrity intact. By measuring across defined test points and assessing for shorts to power within the circuit, key focus areas emerge that may indicate failures. Understanding the role of the wires connecting various components helps pinpoint underlying issues that may not be obvious otherwise. Once identified, undertaking repairs ensures connectivity is restored, while ensuring that the injector control module receives the required signals essential for proper functionality. During Step 18, focus on confirming any shorted wires leading to power reaching the fuel pump connections. Testing the injectors and PCM's ground system ensures that all systems integrate seamlessly with no intersections that could limit functionality. Determining the health of the wiring frameworks enhances reliability while directly impacting the system's overall performance. Should shorts emerge in testing, immediate repairs should be put in place to clear the background noise and dysfunction signs, thereby restoring proper operation flow within the high-pressure fuel pump system. In Step 19, test connections on the injector control module, focusing explicitly on voltage outputs that may indicate broader wiring issues. After confirming test point integrity, evaluate for shorts to ground, while keeping in mind that shorts limit overall functionality. If voltage drops or other abnormalities exist, they warrant thorough inspection and immediate repair actions. Solidifying connections in these areas can greatly enhance overall performance, preventing any discrepancies or risks in critical circuitry that impacts the fuel pump system's efficiency. In the 20th step, examine the continuity status of the HPTI wire concerning ground, while ensuring all precautions are taken to maximize vehicle safety during testing. Gaining clarity into the ground connections proves essential for charting circuit health and enhances overall system performance integrity. If confirmed continuity issues exhibit, repairs in these areas must be executed swiftly to uphold system functionality. Solving ground issues removes potential barriers in the power structure, ensuring dynamic and responsive operation, critical for the high-pressure fuel pump system operational capacities. The final section in the troubleshooting process involves a thorough verification of all repairs made. After conducting the necessary repairs, it is essential to start the engine, observing its performance closely. Ensure there are no remaining diagnostic trouble codes that have reappeared with the HDS scan tool. Successfully resolving the P064A code indicates a proper fix, suggesting that the fuel system is now functioning as intended. It's vital to validate each step to establish that the repairs are effective and maintain vehicle reliability and efficiency. To avoid future occurrences of DTC P064A, regular maintenance should be prioritized, focusing on preventive checks within the fuel system. Regularly inspecting wiring integrity, especially in critical areas susceptible to wear and tear, is key in preemptively addressing potential faults. Replacing parts showing signs of failure, such as the fuel pump or relay, before they lead to critical failures, can also prevent unexpected breakdowns. Keeping the fuel system components clean and well-maintained ensures proper fuel flow and enhances overall engine efficiency. Implementing these preventive strategies can greatly improve the lifespan and reliability of your vehicle's high-pressure fuel pump system. In conclusion, DTC P064A indicates a significant issue within the high-pressure fuel pump system, requiring systematic troubleshooting to effectively isolate and repair the problem. Following the outlined steps ensures comprehensive diagnostics, addressing the root cause rather than just symptoms. Regular maintenance practices enhance reliability, helping prevent the recurrence of similar issues. Understanding the intricacies of how electrical systems and fuel delivery mechanisms interact within the Honda Pilot enhances overall vehicle performance while ensuring longevity. By implementing these guidelines, owners can foster better vehicle health, stability and performance, and reduced concerns regarding fuel system failures. Please like and subscribe to the channel. See you next time.